Find the velocity and position vectors of an object with the given acceleration, initial velocity, and position. The acceleration of the object as a function of time has x and z components. The x component is a1 I hat plus a3. The acceleration of a function of time is given as a1 I hat plus a3 times tk hat, where a1 is the x component given as 2.0 meters per second squared, and a3 is the z component of acceleration given as 1.0 meters per second cubed. And a3 is a coefficient in the z component of acceleration given as 1.0 meters per second cubed. The initial velocity at time t equals 0 seconds is equal to v3k hat, where v3 is the z component of velocity at t equals 0, given as 1.0 meters per second. And the initial position of the object is 0. To begin, let's recognize that this is a two-dimensional motion problem. Being a 2D motion problem, we see that our object is moving in the x and z planes. That's apparent from the components of the vectors they've given us. The acceleration vector is only in the x and z plane. The velocity vector is only along the z-axis. So we could treat this as a two-dimensional motion problem. Let's start with a sketch of the object at our initial time. To do this, I'm going to start with a sketch of the XZ coordinate system. Z is along the vertical axis, X is along the horizontal axis, and our particle, our object, will be represented at the origin at time t equals 0. At that time, the velocity of the object is only along the positive z-axis. We will label this velocity at time t equals 0 v3. Also at this time, the acceleration is only along the positive x-axis. We know that because we see that the z component of the acceleration has time in it. And at time t equals 0, the acceleration's z component is 0, so we only have an x component. I will label this vector right here, the acceleration at time t equals 0, and it's only going to have the x component given as a1. And as given in the problem, our initial position of the object is at the origin. Using this information, we have to determine what the velocity and position vectors of this object is as a function of time. To do this, we're going to begin with acceleration. From the acceleration, we're then going to integrate to get an expression for velocity. And once we have velocity, we're going to then integrate again to get an expression for position. The reason why we could do this is we know that if we take the derivative of position with respect to time, we get velocity. And if we take the derivative of velocity with respect to time, we get acceleration. Since we want to know the velocity function and the position function, and we're given the acceleration as a function of time, then we simply just have to integrate the acceleration to get the velocity followed by the position. So let's begin with the definition of acceleration. Acceleration as a function of time is defined to be the derivative of velocity as a function of time. If we then integrate both sides, the left side from t naught to t, and the right side from t naught to t, where we are integrating with both sides with respect to t, well, we see that on the left side, that just becomes the integral of our velocity at our initial time, our velocity at our final time for the limits of integration, dv of t. And on the left side, we just have to integrate our acceleration function with respect to time. So the acceleration side of this equation, we have to integrate the acceleration function given as a1 I hat plus a3t k hat with respect to time. And on the right side of the equation, we end up with the integral, the definite integral of a velocity differential is just going to be the velocity evaluated at its value at t naught and its value at t. So let's distribute the integration into both components. For the x component, we have the definite integral of a1 with respect to time. And for the z component, we have the definite integral from t naught to t of a3t. So notice the z component is a linear function of time, dt. And that is going to be equal to the velocity evaluated at t, so this would be our function of t, minus the velocity at the initial time t naught. And remember, t naught is equal to 0. Now I forgot my arrow symbols above these quantities for velocity, so I'm going to go back and fix them. Velocity is a vector, and it's important that we remember that. Okay, so integrating the x component, notice the x component of acceleration is a constant. So the integral of a constant with respect to time is just going to be that constant times time evaluated from t naught to t. For the z component is a linear function of time. When we integrate that linear function, we get 1/2 a3t squared evaluated from t naught to t. And remember, t naught is equal to 0. And this is equal to our velocity as a function of time, which is what we're looking for, minus our initial velocity. Now remember, our initial velocity is equal to v3 k hat. Let's go ahead and flip this equation around to put the velocity as a function of time on the left. So our velocity as a function of time is equal to, well, on the right we have v3 k hat plus a1 t minus 0. So that's plugging in the limits of integration for the x component of our acceleration, which I have to go back and put that x component here because I see I forgot to write that. And I have to put our z component here and our z component up here. Okay. So this x component is a1 t minus 0 I hat. And then we have plus 1/2 a3, and this will be t squared minus 0 squared k hat. So let's go ahead and group terms and simplify, beginning with the x component. So with the x component of my velocity, I have the product of a1 times time. For the z component of our velocity, I have the product, or rather, I have the sum of v3 plus 1/2 a3 times time squared. Here is an expression for our velocity as a function of time. Notice how to do this. We start it with acceleration right here, and we integrate it to get velocity as a function of time.